Welcome to today's Trane Engineers Newsletter Live program. I'm Jeanne Harshaw, and this program will focus on building pressure control, which involves controlling the static pressure difference between inside a building and outdoors. Space-to-space pressure control, which is used in some healthcare and laboratory applications, is outside the scope of today's program. Building pressure control can be easily overlooked, but it's very significant to building operation. Poor building pressure control can hinder HVAC system operation and interfere with proper building control. Today, we're going to talk about building pressure and why it needs to be controlled. Then we'll explore common building air relief systems. And finally, we'll discuss the advantages and drawbacks of relief versus return fans. To cover the topic today, we have Trane application engineers Chris Hsieh, John Murphy, and Eric Sturm. So Eric, please give us an overview of why building pressure control is important.
Building pressure control is important for two key reasons. First, the right level of building pressure helps make the building comfortable and protects it from damage due to moisture. Second, excessive building pressure, either positive or negative, produces physical forces and unplanned airflows that can cause poor building operation. If indoor static pressure is greater than outdoor static pressure, the building is positively pressurized. What we're talking about is controlling the pressure differential between inside and outside a building. This pressure difference is a function of how much air enters the building compared to how much air is removed from it. Positive building pressure pushes outward on doors and windows. Positive pressure also causes exfiltration, where indoor air moves out of the building through small holes and cracks in the envelope, and through doors and windows. Too much positive pressure can become a problem. Outward swinging doors can stand open, which could create a security problem. Inward swinging doors can be difficult to open because the building pressure is pushing against them. In the HVAC system, too much positive pressure can reduce outdoor air intake airflow, resulting in inadequate ventilation. In addition, positive space pressure can reduce supply airflow and could result in space comfort issues. But there are times that a little exfiltration caused by positive building pressure is a good thing. For example, when the outdoor air humidity is high, exfiltration of dry indoor air helps keep the building envelope dry. But in the wintertime, excessive exfiltration of moist indoor air can lead to condensation on cold surfaces inside the walls, which can lead to microbial growth, corrosion, and structural damage. On the other hand, if indoor static pressure is less than outdoor static pressure, the building is negatively pressurized. Negative pressure pulls inward on doors and windows, and it can cause infiltration of outdoor air through the envelope into the building. Like before, a little inward force on doors and windows is okay, but too much can be a problem. Outward swinging doors can become difficult to open, and inward swinging doors tend to stand open, which could affect building security. In fact, the Americans with Disabilities Act and building codes set limits on door opening force. Too much negative pressure reduces exhaust fan airflow, which can result in poor ventilation. In the summertime, infiltration of moist outdoor air can lead to condensation on cool surfaces within the building envelope. Hidden condensation increases the potential for microbial growth and material damage. It also increases the space latent load. A little infiltration may be helpful in the winter when outdoor air is dry because it helps to keep the building envelope dry. But substantial winter infiltration can cause cold drafts and discomfort due to poor temperature control. Additionally, cold areas in the space and ceiling plenum pose a condensation risk. And of course, infiltration of cold air increases the heating load. Generally, three things impact building pressure: HVAC, weather, and wind. Let's start with HVAC and a review of typical airflows into and out of a building with a multiple zone VAV system. From the HVAC side, outdoor air mixes with recirculated air from the building in this air handling unit. This air mixture passes through a filter, heating coil, and cooling coil. Supply fans distribute it through ductwork to VAV boxes and finally into the occupied spaces. At the same time, air naturally moves from areas of higher pressure to areas of lower pressure. In this diagram, the air handler has a relief fan exhausting air out. There are other methods to relieve air from the building that we'll discuss later. Some zones may have separate exhaust systems to remove stale air. Common examples include bathrooms, locker and shower rooms, kitchens, salons, and art classrooms. Now let's look at the building side. There may be infiltration when the pressure outside of the building is higher than inside. Untreated ambient air can enter the building through doors, windows, or a leaky building envelope. Or the building can experience exfiltration when the pressure inside the building exceeds the level outside, causing air to leak through doors, windows, and the envelope outward. The amount of outdoor air entering the system can vary throughout operation. Systems often employ demand-controlled ventilation to decrease the ventilation rate during periods of reduced occupancy. As a result of this, the amount of outdoor air being introduced into the system may vary from hour to hour. Consequently, to maintain building pressure, the exhaust or relief system must also change the amount of air being removed. Additionally, airside economizing can be used to reduce system energy usage by introducing cool outdoor air to partially or fully offset space loads. Like demand-controlled ventilation, the amount of outdoor air introduced is variable. Economizers can operate in two modes, modulated and integrated. Here's a chart which illustrates VV system operation. System air flows along the vertical axis, while load is on the horizontal axis. Starting at the left side, our VV system is heating. As the demand for heat decreases, the supply airflow in gray is reduced. Return airflow in orange decreases, following the same slope. The black line indicates outdoor airflow. During the heating mode, this rate stays constant at the minimum required for ventilation. The heating load is now gone, and we're at minimum cooling load. So our system begins modulated economizer operation. As the cooling load increases, the system responds by increasing the supply of cool outdoor air. The amount of recirculated return air decreases as the amount of outdoor air increases. This continues in integrated economizer mode, where mechanical cooling supplements economizer operation until the outdoor air conditions reach the economizer high limit shutoff. Now the system will revert the outdoor air damper back to its minimum setting for ventilation, and mechanical cooling will be used to offset the cooling loads. When we think about building pressure control and an air relief system, it's important to remember the amount of outdoor air can be variable, in this case due to economizer operation. Therefore, the amount of air leaving the building must also vary to maintain desired building pressure. So that covers the HVAC factors. The next factor we'll look at is stack effect. When the outdoor air is warmer or colder than the indoor air, the resulting difference in density causes pressure difference that varies with building height. As a result, this is a weather-dependent pressure difference. Consider a simple 5-story building in Brooklyn. During cold weather, the more dense outdoor air infiltrates at lower floors of the building. Then, warm, less dense air rises inside the building and exfiltrates at the upper floors. The neutral pressure level, the point where indoor pressure is equal to outdoor pressure, is near the middle of the building. During hot weather, the opposite occurs, but is less often noticeable because the indoor to outdoor temperature difference, and therefore the density difference, is not as extreme as during cold weather. Stack effect is usually insignificant in shorter buildings, but very important in taller buildings. And the third factor I mentioned was wind. Blowing wind exerts velocity pressure on the windward side of a building, while depressurizing the leeward side. In essence, the wind changes the effective outdoor static pressure. It tends to push outdoor air into the windward side of the building and pull indoor air out of the building on the leeward side. Wind may have little impact on a short or low-rise building in the middle of a city, but it might have a greater impact on a taller building or a poorly sheltered building in the middle of an open area. I've explained that excessive pressure, either positive or negative, can be bad. So what should the building pressure be controlled to? When it's hot and humid outside, most designers agree that building pressure should be slightly positive. This is because exfiltration of dry indoor air minimizes the risk of humid outdoor air leaking into the building envelope. But when it's cold outside, many designers agree that building pressure should be neutral, or maybe even slightly negative. A little bit of infiltration of dry outdoor air keeps moist air from leaking into the building envelope. In most cases, a pressure difference of 0.05 to 0.1 inches of water is sufficient to get the benefits of pressure control without the problems. But this can vary by application, so it's important to understand what causes this pressure difference between indoors and outdoors and why it changes. We've included a previously published engineer's newsletter in the bibliography, and it explains in an example how to calculate these effects and determine the desired building pressure set point when wind or stack effect are of concern.
Thanks for that introduction, Eric. In this next section, we will discuss some of the most common system configurations used for controlling building pressure. To help demonstrate, we have a plexiglass model building with a roof-mounted air handling unit. John, can you introduce us to this model?
We'll use this model to demonstrate some of the concepts related to building pressure control. This lower box is our building. It's about 3 feet by 2 feet and 2 feet tall. There's even a door in the front with a latch. Now, the volume of this building is small relative to the fan CFM, so pressure changes will occur faster than in a real-life building, but that makes it better for demonstrations like this. Then we have our air handler mounted on the roof, which is in 2 parts. This fixed module on the left includes a supply fan that blows directly into the building. No budget for ductwork on this project, so it's direct discharge. In a real air handler, of course, you'd have coils and filters right here. This other module on the right is replaceable, so we can switch it out to demonstrate other system configurations. For the first demo, it's just a mixing box with an outdoor air damper mounted on the end and a return air damper on the bottom. The opening in the roof of our building aligns with the air handler's return air damper. Again, a pretty short return air path. Now we use this differential pressure gauge so you can visualize how the pressure changes. This is a Dwyer Magnehelic and it has 2 ports on the side. The tube attached to the high side port is routed down through the hole in our building. The tube attached to the low side port is connected to this red probe located outside the building. I'll talk more about this red device later. So this gauge measures the difference between the static pressure inside our model building and the pressure outside. The orange needle indicates the current measurement, and the gauge ranges from a positive 0.5 inches of water to the right side down to a negative 0.5 inch to the left.
The first approach we'll look at for controlling building pressure is actually to do nothing at all. We refer to this as natural relief. Just let the air leave the building naturally. The air handler brings in outdoor air for ventilation. There might be some local exhaust fans to remove air to help balance with this intake airflow, but the remainder leave the building by exfiltration. Buildings are not airtight, so they have some capability to naturally relieve excess air through cracks in the building envelope, as well as through doors and around the windows. John and Eric, can you demonstrate how natural relief works?
To demonstrate natural relief, we'll first turn on the supply fan. Right now, Eric has the return air damper fully open and the outdoor air damper fully closed. So this is recirculating only mode, such as maybe like during morning warm-up. With air just recirculating and no outdoor airflow being brought in, the difference between the indoor and outdoor pressure should be 0 or neutral. But you see that the needle reads just a bit positive, probably because the outdoor damper is not leak tight. Next, I'll have Eric open the outdoor damper to minimum position to bring in code-required ventilation. You can see that bringing in some outdoor air causes the pressure to rise a bit so the building is positively pressurized. Relief air is leaking out somewhere through cracks at the edges or around the door. This is natural relief. Next, let's see what happens on a mild day when airside economizing. I'm going to have Eric modulate the outdoor damper to fully open and the returner damper fully closed. And you see that the needle pegs. Building pressure is overly positive. The air handler is trying to bring in 100% outdoor air for economizing, but the building is not leaking enough to relieve all that air, so building pressure rises dramatically. If I unlatch the door to go inside, you see that the door pops open and remains standing open. It's difficult to close. Relief air is blowing out the door, so the gauge doesn't read as high a pressure. When I shove the door closed and latch it, we see that the building pressure has pegged again.
Natural relief may prevent excessively positive pressure in small, less tightly constructed buildings, especially if they have constant local exhaust fan operation and no airside economizer. The obvious benefit is no added cost for components or controls. However, the building may still experience fluctuations in pressure due to some of the other influences we mentioned, and especially if an airside economizer is used. Buildings constructed with tighter envelopes might not offer adequate natural relief and could then be overly pressurized most of the time.
Instead of this do-nothing approach relying on natural relief, the HVAC system can be used to control building pressure. Theoretically, you can vary either intake airflow or relief airflow, but most designers choose to vary relief airflow because intake airflow must be maintained for proper ventilation per building code. So we will focus on varying relief airflow in this program. This next approach uses a non-motorized gravity-operated relief damper, commonly called a barometric relief damper. In this case, this damper is installed in or very near the occupied space, such as an open ceiling plenum, like shown here. Again, the air handler brings in outdoor air for ventilation, and local exhaust fans might remove some of this air to somewhat balance this intake airflow. As the positive pressure inside the building increases, the barometric relief damper is forced open, allowing air to leave the building and preventing the building pressure from becoming overly positive. Now let's watch John and Eric demonstrate this with the building model.
Over here in the side wall of our model building, we have a real but very small barometric damper. It's hinged and counterbalanced so it hangs closed. It was latched shut for the first demonstration, but for this one I've unlatched it so it's allowed to open. To demonstrate barometric relief, we'll start the fan again in recirculating mode. That is, return damper fully open, outdoor damper fully closed. As Eric opens the outdoor damper to minimum position, again, building pressure rises a bit. Not enough pressure to force open the barometric damper yet, so right now just natural relief is happening. But now let's go to economizer mode. Outdoor damper fully open, return damper closed. The building pressure rises further, high enough to force the barometric damper open so it now relieves the excess air. For this model, we sized and selected this damper to relieve the required CFM at 0.2 inch of pressure. With barometric relief, the building is still under a positive pressure, but not nearly as high as when we relied on only natural relief.
Local barometric relief may be suitable for preventing overly positive pressure in small buildings, especially if they're used with an open ceiling plenum for return air. They're often well suited for large manufacturing and warehouse buildings that have a lot of usable wall area. They're relatively inexpensive and require no additional controls or pressure sensors. However, it's important this damper be properly sized, large enough to relieve sufficient airflow to prevent overly positive building pressure. And dampers may be needed on multiple faces of the building to minimize the effects of wind. Because the relief dampers are typically located in the conditioned space or in the open plenum near the space, they create an opening in the building envelope, increasing the risk of unwanted air leakage. So, good seals, insulation, screens, and proper adjustment of the counterweight are all important.
To reduce the cost and headaches associated with installing one or more local relief dampers, some designers have attempted to use single barometric relief dampers located in a roof-mounted air handler or packaged rooftop unit. We are calling this configuration a central barometric relief damper. This relief damper must be located in the return air path upstream of the return air damper. This allows this section of cabinet to be at a positive pressure to force relief air out of the building, while the mixing box remains at a negative pressure to draw in outdoor air for ventilation. When the pressure in this return air plenum increases high enough, the barometric relief damper is forced open, allowing the air leaving the building. Systems that use this approach tend to experience higher building pressures. The combined pressure drop through the return air grill, ceiling plenum, any return ductwork, and the return air openings to the air handler might be 0.2 of an inch, or might be even up 1 inch or more. This means that the space must be overpressurized by this amount before the central barometric relief damper even cracks open. Since we have just demonstrated this barometric relief damper, we'll skip the demonstration and let Eric explain the benefits and drawback of this configuration.
Centralized barometric relief is tempting since it's easily packaged in roof-mounted equipment, does not involve any openings in the building envelope, and needs no controls or sensors. It works better than natural relief, but the added pressure drop of the return air path and the fact that there is typically very little room available for this damper in the small roof-mounted equipment results in this approach often relieving air only under very positive pressure conditions. So air still finds less restrictive ways to leave the building, like through the doors. And if the wind blows against this damper, it makes it even more difficult to relieve excess air and building pressure rises further.
So those are two configurations that use dampers for relief. Now we'll move on to some configuration that use an additional fan for relief. The first is to add a central relief fan, like the central barometric relief damper. This relief fan must be located upstream of the return air damper. When it operates, it forces relief air out of the building. In general, there are two ways to control this fan. The first method is to simply turn a constant speed relief fan on whenever the outside air damper opens beyond a predetermined threshold. During much of the year, when the system is bringing in minimal outdoor airflow for ventilation, local exhaust fans and natural relief are often sufficient to relieve the excess airflow and avoid overly positive building pressure. In this case, the relief fan is shut off. But when the outside air damper opens further for airside economizing, this relief fan is turned on, forcing excess air out of the building and preventing overpressurization. John and Eric will demonstrate.
Here we've changed this second module in our air handler, replacing the mixing box with this module, which includes an outdoor air damper on the top and a return air damper here inside. But now this one includes a relief fan that can blow air back outside the building. Return air is drawn out of the building into this chamber. Here the air then either recirculates through the return air damper or is blown outside by the relief fan. The recirculated air mixes with the outdoor air in this mixing box and is then drawn into the supply fan delivery to the building. Let's demonstrate the on-off control method for this relief fan, which Chris just introduced. We turn on the supply fan, and Eric has the damper set again for recirculating only mode. Note that I relatched the Barometric relief damper in this side of the building, so it won't open for any of our remaining demonstrations. As Eric opens the outdoor damper to minimum position, again, building pressure rises a bit. The relief fan is still turned off, so we're just relying on natural relief so far. Now let's try economizer mode. When Eric closes the return air damper and fully opens the outdoor damper, you see that building pressure rises further. But with this control strategy, as soon as the outdoor damper begins to open for economizing, I turn on the relief fan. This forces the excess air out of our building, preventing it from being overpressurized.
This on-off control strategy prevents overpressurizing the building during airside economizing. The relief fan and controls can be easily packaged in an air handler or rooftop unit. And no additional pressure sensors are required. As Chris mentioned, the relief fan is turned on and off based upon the position of the outdoor damper. This often allows the fan to be turned off for many hours during the year, saving energy. However, on-off control of a constant speed relief fan means that the building will likely experience some fluctuations in pressure due to the other factors I explained, and may even experience negative pressure during some parts of modulated economizer operation. So, proper sizing and air balancing of this relief fan are critical to avoid too positive or too negative building pressure.
A better way to control this relief fan is to measure building pressure directly and then modulate the capacity of the relief fan to maintain this pressure in a desired range. In this case, the pressure sensor measures the difference between the indoor and outdoor static pressures. If the pressure difference rises above the desired limit, the relief fan turns on and a VFD modulates its speed to relieve sufficient airflow to maintain building pressure at the desired set point. If the major pressure difference drops below set point minus some deadband, the relief fan can be turned off. Directly measuring building pressure allows the system to respond to changes and actively control pressure in a more stable fashion. John and Eric will demonstrate.
We still have the same configuration as before, with a relief fan that's used to force excess air out of the building. For this demonstration, both the supply fan and relief fan are already running, with the outdoor damper open to minimum ventilation position. Note that each fan has a knob we can use to vary its speed so we can mimic VAV operation. Right now, the speed of the relief fan has been adjusted to maintain building pressure at the desired set point, which is 0.05 inch of water in this case. Now, Eric will modulate the outdoor damper further closed to simulate demand-controlled ventilation. You see that the building pressure starts to go negative as the system brings in less outdoor air. But I respond to this by slowing down the speed of the relief fan until building pressure is again slightly positive at our desired set point. Now let's show economizer mode again. Outdoor damper fully open, return damper closed. Building pressure rises as the system brings in more outdoor air. So I respond this time by speeding up the relief fan even further to force excess air out of the building and bring the building pressure back down to set point.
Modulating the central relief fan can provide very stable control of building pressure. It allows the HVAC system to respond to changes due to airside economizing, demand-controlled ventilation, wind, stack effect, or local exhaust fan operation. And it allows you to change the set point during summer versus winter operation. Oftentimes, it affords more layout flexibility than a return fan, which we'll discuss next. This is because a relief fan can be positioned anywhere along the return air path, while a return fan must be located between the nearest zone and the air handler. With this control method, proper location and selection of the indoor and outdoor pressure sensor is important for stable control. We'll discuss this a bit later in the program. And a relief fan might not be suitable for those systems with a very high return path pressure loss. This might be the case if the return air is fully ducted, if flow control devices are installed in the return air path for space-to-space pressure control, or if high-efficiency filters are installed at return air grills. If the supply fan is unable to overcome the combined pressure loss of the supply and return air paths, a return fan may be necessary.
The final configuration we'll look at today uses a central return fan. Like the relief fan, the return fan must be located upstream of the return air damper, but what's different is that it is in the return air path, so it is in series with and assists the supply fan. In this configuration, the supply fan must create high enough pressure at its outlet to overcome the pressure losses associated with the supply air path. However, the pressure at the inlet of the supply fan only needs to be low enough to overcome the pressure losses internal to the air handler. The return fan is used to overcome the external pressure losses associated with drawing return air out of the zone through the grills and ceiling platen or return ductwork and into the air handler casing. It must also generate enough pressure at its outlet to force relief air out through the relief damper. Like the relief fan, there are various methods that might be used to control this return fan. The first is sometimes used in constant volume systems. It involves simply turn on a constant speed return fan whenever the constant speed supply fan is on. Since both supply and return fan operate at a constant speed, the system can usually be balanced to prevent building pressure from becoming too positive or too negative. However, it can still fluctuate due to the other influences Eric mentioned. More commonly, you can find return fan used in larger systems, which tend to be VAV. In this case, controlling the return fan is not as simple. Air balancing alone won't help because the supply fan airflow and therefore the required return fan airflow is always changing. In a VAV system, some designers specify airflow tracking to indirectly maintain building pressure. An airflow measurement device is used to measure the current supply airflow. Then a controller subtracts a CFN offset to compensate for air that leaves the building through the local exhaust fan and exfiltration. This offset is subtracted to calculate the current return airflow set point. A second airflow measurement device is then used to measure return airflow, and a VFD modulates the speed of the return fan to maintain the return airflow at this calculated set point. With this approach, building pressure might be able to be indirectly controlled. Since we don't have airflow measurement in our model, we'll let Eric share the benefits and drawbacks directly without going through a demonstration.
As Chris mentioned, in a system with a very high return path pressure loss, a return fan might be needed to overcome the pressure loss of the return air path and assist the supply fan. This often allows for the use of a smaller supply fan motor than if a relief fan was used. But the overall fan power may not be lessened. That depends on several factors. Airflow tracking works best in buildings that have constant local exhaust and are only minimally affected by wind or stack effect. But this method of indirect control can still result in fluctuations in building pressure due to these external influences. And making this work requires two very accurate and well-calibrated airflow measurement devices. This is because the difference between supply and return airflows can be a relatively small fraction of the measured supply airflow. Finally, as I explained earlier, layout options are somewhat limited. Since the return fan draws air from the spaces, it needs to be located between the nearest space and the return air damper. Depending upon the building layout, where relief air exits the building, this may or may not be that big of a challenge. Incidentally, some designers will try fan speed tracking as a method for controlling the return fan. In this case, the return fan's speed is adjusted to operate at the same speed as the modulating supply fan. This approach doesn't tend to work very well because the supply and return fan curves are not identical. When this approach is used, we tend to see wide fluctuations in building pressure in all but the leakiest of buildings.
A better way to control this return fan is, again, to measure building pressure directly. With the control method, the position of the relief damper is modulated to maintain measured building pressure at the desired set point. Then the return fan speed is modulated to maintain static pressure set point in the return air path downstream of this return fan. As the relief and return air damper modulate over the course of the system operation, the static pressure in this portion of the return air plenum will change, so the return fan speed will adjust. Eric and John will demonstrate this one.
Here we've changed this second module of our air handler again. This new module is equipped with a return fan, which is in series with a supply fan. This return fan draws air out of the building and pressurizes this chamber here. This air then either recirculates through the return air damper or exits the building through this modulating relief damper. Again, the recirculated air mixes with outdoor air in this mixing box and is then drawn into the supply fan. We've added a second pressure gauge to measure the pressure in this return air section of the air handler. As Chris mentioned, this pressure can be used to modulate the speed of the return fan. For this demonstration, we have both the supply and return fans already running with the outdoor air damper at minimum ventilation. If Eric modulates the relief damper further closed, you can see that building pressure rises. But this also increases the pressure in this return air plenum, which will require the return fan to slow down. Changing the position of the relief damper and the speed of the return fan at the same time both cause building pressure to change. So Eric and I have our hands full finding the right balance point to settle out. This is why control of a return fan in a VAV system gets more complicated, because it requires proper tuning of these interacting control loops.
This control method can provide stable control of building pressure when a return fan is used, because it allows the system to compensate for changes due to airside economizing, demand-controlled ventilation, wind, stack effect, or local exhaust fan operation. It also allows the building pressure set point to be changed seasonally if desired. The drawback is that the approach requires an additional pressure sensor mounted in the return air plenum of the air handler, and for this control loop to be coordinated with the rest of the unit controls. Finally, like with a modulating relief fan, proper location and selection of the indoor to outdoor pressure sensor is critical.
We have covered a lot of ground, so let's recap. Barometric relief can work in smaller leaky building. A relief damper located in or near the occupied space works better than an undersized central barometric relief damper. Using the relief fan is preferred. On-off control of this relief fan often works well in systems with constant volume or two-speed fan control and airside economizers. But direct measurement of building pressure and using this to modulate the central relief fan offers much better control. This is particularly important in systems with variable speed, supply fan control, or demand control ventilation, or if external factors like wind, stack effect, or variable operation of local exhaust fan play a significant role. If the system has very high return path pressure loss, such as return fan must be used, modulate relief damper based on major building pressure, and modulate return fan to maintain the return air plenum pressure at set point. As we mentioned, return fan airflow tracking seems to work well enough in some cases, but requires very accurate flow measurement devices.
Whether a relief fan or return fan is used, the preferred method of control involves directly measuring building pressure. To do this, two tubes are connected to an electronic pressure transducer. One tube is routed to a location inside the building, and the other tube is routed to the outdoors. The transducer measures the pressure difference between these two locations and converts it to an electrical signal that can be used to modulate either a fan or a damper. Now, the key in measuring building pressure is stability. You rarely want the control system to respond rapidly to changes in building pressure. So the electronic transducer dampens any fast-acting changes to improve stability and minimize hunting. Now, the indoor tube is typically routed to a location on the ground floor of the building because the effects of over or under pressurization are usually most noticeable at the exterior doors. A large open space or a central hallway is usually a good location. You want to avoid any location where it might be affected by wind gusts, so not too close to an exterior doorway. As I mentioned, the other tube needs to be routed to the outdoors. This requires it to be protected from wind gusts as well as from getting plugged with water or debris. This red device, which I pointed out earlier, is an outdoor probe that we've had excellent experience with for decades. The tube is connected to the top, and the bottom is open 360 degrees. When installed in this correct orientation, it prevents water and debris from plugging the tube and minimizes the impacts of wind gusts. I'll use this magnehelic to show how effectively it works. First, with the open tube, you see how the wind blowing affects the needle. Now, when I plug the tube into this red probe, watch how this 360-degree opening protects it from wind gusts. Now, often, this outdoor probe is attached to the building or mounted on the HVAC equipment itself, as shown here on the top of this rooftop unit. You want to put it in a location where people will not tamper with it and not too close to vertical surfaces so that you don't get localized pressure pockets caused by blowing wind.
ASHRAE's Energy Standard 90.1 has several sections that cover building pressure control. First, there are requirements which discuss the use of an economizer. Designers might choose to use an airside economizer to satisfy the requirement. The standard requires the usage of a mean to relieve excess outdoor air to prevent overpressurizing the building. Notice that the standard does not specify the type of system to be used. The standard also discusses the location of the relief air outlet in relation to the outdoor air intake. Standard 62.1, ASHRAE's ventilation standard, provides guidance on minimum separation distance between intake and exhaust for different system configuration and types of exhaust. Standard 90.1 provides some additional requirement if the system uses a return or relief fan to remove excess air from the building. First, the system must either directly or indirectly control building pressure. Direct control means system measure indoor and outdoor pressure to maintain the desired pressure differential. Indirect control means the system measure the supply and return airflow rates to maintain a desired differential. There are additional requirements related to maximum energy consumption. There are also several exceptions for relief or return fan systems with small horsepower values and staged relief fans.
So that's our overview of building pressure control. We hope you found it a helpful way to learn about this topic. As always, the bibliography included in your handout provides more information on where to find a number of resources related to today's topic. Or contact your local Trane account manager for specific information on Trane systems, equipment, controls, and services. For those of you seeking continuing education credit, check out the newest online courses offered on Trane Education Center, free and on demand. And please don't forget to fill out a survey to let us know what you thought of today's program. AIA members, turn in your member information to your local office, or if watching online, send your information to enl@trane.com. And finally, for those of you viewing in person, please ask your local host about details for the remaining Engineers Newsletter Live programs. The yearly program lineup can also be located at www.trane.com/enl. Thanks for joining us today. We look forward to seeing you next time.